There is this fundamental assumption that we make every single morning when we just like roll out of bed.
Right.
Your feet hit the floor and the floor is just there. It holds you up. If you knock your coffee mug off the table, it shatters on the ground.
Yeah, we rely on it completely.
Exactly. We treat gravity as this clean, simple, binary tether. But the actual architecture of the universe that you are standing in right now listening to this is built on this foundation of, well, Riemannian geometry and four-dimensional space-time.
Which is incredibly fluid.
Right. Fluid, dynamic, and constantly at war with quantum mechanics. We think of gravity as a rigid floor when mathematically it's far closer to a turbulent ocean.
I mean, the human brain is naturally engineered to prefer Euclidean geometry.
Which means what exactly for
Yeah.
the listener?
It means we like flat planes, we like straight lines, predictable forces.
Mhm.
But the moment you zoom out to the cosmological scale or, zoom all the way into the subatomic scale, that comforting, predictable floor just completely liquefies. Yeah, it's gone. The deeper you look at the actual mechanics of space-time, the more you realize that our everyday intuition about how reality operates is not just slightly inaccurate. It's fundamentally backwards.
And that is exactly why today we are stripping away the sci-fi tropes. We're looking at the terrifying thrill of overturning like 80 years of accepted physics.
It's a huge shift.
Massive. We are unpacking the work of gravity physicist Claudia de Rham. She's a researcher who looked at a mathematical bedrock that the smartest minds on Earth had accepted for almost a century and realized, it might be completely flawed.
Which takes incredible bravery, by the way.
Oh, absolutely. So on this deep dive, we are going to explore the literal quantum origins of the cosmos. We're going to dissect the mathematical impossibility of those anti-gravity rumors you see all over the internet.
Right, the Reddit rabbit holes.
Yeah, we'll get into those. And we are going to dive into extra dimensions, massive gravitons, and the holographic nature of black holes. Our mission for you on this deep dive is to explore the absolute limits of our universe and, frankly, the limits of the human minds trying to map it.
Because it requires a profound willingness to just abandon your preconceived notions.
Ah.
I mean, to understand what de Rham achieved and to really grasp the current frontier of theoretical physics, we have to recognize that the established dogmas of science are only as solid as the assumptions they're built upon.
Right, the foundation.
Exactly. When you tweak one underlying assumption, the entire structure of reality has to be renegotiated.
So let's start that renegotiation right now with the most, I think, pervasive myth in popular astrophysics, which is anti-gravity.
Oh, boy.
Right? I mean, you can't go down a forum or a comment section without hitting a thread about clandestine organizations, places like DARPA, or those tic-tac UFOs.
Right, the Navy videos.
Yeah. Allegedly utilizing anti-gravity tech. Craft floating silently, defying inertia, operating with no thermal exhaust. But to a theoretical physicist like yourself, the very term anti-gravity is, well, it's fundamentally nonsensical, right?
It really is. It relies on a completely outdated Newtonian hangover of how gravity works.
A hangover. I like that. Explain that Newtonian view.
So the Newtonian potential views gravity strictly as a vector of attraction between two masses. It is a force acting across a distance, like a rope pulling you down.
Right, an invisible tether.
Exactly. And if you view gravity through that lens as a downward pulling force, then it makes intuitive sense that you could, engineer an upward pushing force to counteract it or build a shield to block it.
Like an anti-gravity drive.
Right.
Yeah.
But Albert Einstein's general relativity completely obliterated that concept in 1915.
Over a century ago.
Over a century ago. Yeah, gravity is not a force propagating through space. Gravity is the geometry of space-time itself.
Okay, wait, let's hover there for a second. Gravity is the geometry itself.
Yes. The presence of mass and energy dictates the curvature of the space-time manifold. And that curvature dictates how mass and energy move.
Right, which is why we really need to move past that overused high school analogy. You know the one.
The bowling ball on a trampoline.
Yes, the bowling ball. Because the trampoline implies a two-dimensional fabric being pulled down by some external mysterious gravity into a third dimension.
Yeah, it implies gravity is acting on space-time rather than being space-time.
Exactly. Space-time is a four-dimensional manifold. General relativity utilizes the metric tensor to describe how distances and times are measured in this curved geometry.
Right.
You can't just flip a switch and turn off a metric tensor. You can't have an anti-gravity drive because you cannot simply, delete the geometry of the space you are currently occupying.
That tensor calculus is precisely the barrier. I mean, the Einstein field equations, they equate the curvature of space-time on one side of the equation to the stress-energy tensor on the other.
Okay, break down the stress-energy tensor for me.
Sure. So every form of energy, every ounce of momentum, every instance of pressure or shear stress in a given region, all of that contributes to the curvature.
It's all accounted for.
Exactly.
Yeah.
So to create anti-gravity in the sci-fi sense, you wouldn't just need negative mass, which, by the way, violates the weak energy condition. You would need to locally flatline the curvature of space-time while still existing within it.
Which makes no sense.
No, the mathematical gymnastics required to achieve that result in immediate catastrophic paradoxes.
But let's actually follow the logic of that stress-energy tensor for a second, because this leads to a thought experiment that I absolutely love.
Okay, let's hear it.
So if all energy and mass are interchangeable, right, Einstein's famous E equals mc squared,
Right.
and all energy contributes to the curvature of space-time, well, human thoughts are just electrical impulses. They require metabolic energy, which translates to electrical energy in the brain. Does that mean a highly anxious overthinker is literally mathematically warping the geometry of the universe with their thoughts?
Well, when you look at the strict, rigorous mathematics of general relativity, the answer is undeniably yes.
I know it.
I mean, your brain is utilizing localized energy to process those electrical signals.
Right.
According to the stress-energy tensor, that concentration of energy creates an infinitesimally small, localized distortion in the space-time manifold right around your head.
That is wild.
It gets better. Because those electrical signals are actually moving, you are also inducing an impossibly microscopic version of frame dragging.
Frame dragging, like black holes do.
Yeah, exactly. The lens-thirring effect, where the rotation or movement of mass energy slightly twists the space-time fabric around it.
Oh, wow.
Now, obviously, the gravitational effect of human anxiety is dozens of orders of magnitude too small to ever measure. But fundamentally, the mechanics apply. You are literally bending the universe by thinking about it.
I feel incredibly validated by that. My anxiety actually has a gravitational footprint.
It absolutely does.
But, understanding that every localized pocket of energy bends space-time helps explain why popular culture fundamentally misunderstands dark energy.
Oh, dark energy is so misunderstood.
Right, because people hear that the expansion of the universe is accelerating, that galaxies are being pushed apart. And they just assume dark energy is the anti-gravity they've been looking for.
Yeah, they think it's a repulsive force breaking Einstein's rules.
Exactly. But it's not, is it?
Not at all. It is a critical misclassification. Dark energy does not violate general relativity. It is deeply embedded within it.
Okay, so how does it work then?
Well, in the cosmological models, dark energy is often represented by the cosmological constant. You'll see it as the Greek letter lambda.
Right, lambda.
What is counterintuitive about it is its equation of state. Dark energy has a positive energy density, but it exerts a negative pressure.
Negative pressure, that sounds weird.
It does, but in the mechanics of the metric expansion of space, this uniform negative pressure causes the fabric of the universe itself to stretch.
So it's not anti-gravity actively pushing two galaxies away from each other through space.
Right, exactly.
The galaxies are essentially just sitting still in their local space-time coordinates, but the coordinate grid itself is stretching, generating more space between them.
That's a great way to put it. Dark energy is surfing the exact rules of Einstein's geometry. It just operates with variables that are utterly alien to our localized planetary experience.
It plays by the rules perfectly.
It plays by the rules flawlessly. And, we already utilized the bizarre geometric rules of gravity to our advantage without needing any hypothetical sci-fi technology.
You mean like orbital mechanics?
Yeah, gravitational slingshots. Look at when we send a probe, like Voyager or Cassini, toward Jupiter.
Right.
To an observer who doesn't understand orbital dynamics, the probe approaches a massive gas giant, speeds up immensely, and then shoots away instead of being swallowed.
Right, it looks like magic. It looks like it is defying the gravity of Jupiter.
But the mechanics are just an exchange of angular momentum. The probe enters Jupiter's gravitational well, but because Jupiter is moving in its orbit around the Sun, the probe essentially steals a microscopic fraction of Jupiter's orbital kinetic energy.
Wow.
It surfs a curvature of space-time that Jupiter drags along with it, accelerating the probe while slowing Jupiter down by an immeasurable infinitesimal amount.
That is just a masterful exploitation of space-time geometry.
Absolutely.
But, as we try to map these curvatures across the cosmos, we run into this massive invisible elephant in the room.
Dark matter.
Dark matter. Because when we look at galactic rotation curves, I think this was originally analyzed by astronomers like Fritz Zwicky and later Vera Rubin. We see stars at the outer edges of galaxies moving way too fast.
Way too fast.
Right. The visible matter, the baryonic matter that we can actually see emitting light or X-rays, it simply does not possess enough mass to generate the gravitational curvature required to keep those outer stars tethered.
If we only relied on visible matter, the galaxies should literally be flying apart.
Which means there has to be a massive amount of unobservable mass creating these deep gravitational wells that actually hold the galaxies together.
Yes, but, the term dark matter almost feels like a placeholder.
Like a mathematical stopgap.
Exactly. When you actually dig into the literature, specifically the concept of the dark sector, it gets vastly more complex.
How so?
We aren't just talking about, dead stars or rogue planets that are hard to see. We are talking about exotic particles, weakly interacting massive particles, WIMPs, axions, sterile neutrinos.
Whole zoo of particles.
Yeah, a completely parallel structure of matter that only communicates with our reality through gravity.
It is a profound paradigm shift. So the dark sector could be as rich and varied as our standard model of particle physics.
Theoretically, yes.
Yeah.
But because it doesn't interact with the electromagnetic force, it is completely invisible to us.
Because light is electromagnetism.
Right. It doesn't absorb light. It doesn't reflect it or emit it.
Yeah.
You could have a dense cluster of dark matter passing directly through our solar system right now, and the only way we could theoretically detect it is through incredibly sensitive measurements of its gravitational interference.
This actually opens up a highly speculative yet mathematically valid avenue that Claudia de Rham's research touches on.
The dark structures.
Yes. If there is a massive amount of dark matter in our galaxy exerting gravitational force, could there be dark matter structures? Like dark matter planets, or this is where it gets crazy, a dark matter civilization sitting right here in this room with us, completely imperceptible to our eyes and instruments?
It is a phenomenal question. And it really bridges physics and philosophy.
Right.
Because if the dark sector has its own internal fundamental forces, like perhaps a dark electromagnetism that governs how dark particles interact with each other, then theoretically complex structures could form. But the prevailing skepticism in the astrophysics community comes down to the mechanics of dissipation.
Okay, break that down. Explain dissipation in this context. Why couldn't dark matter just clump together and build a dark skyscraper?
So for standard baryonic matter to form structures like stars, planets, or skyscrapers, it has to be able to clump together.
Right.
When particles of normal matter collide and condense, they shed their excess kinetic energy by emitting photons. This is called bremsstrahlung, or breaking radiation.
So they bleed off energy.
Exactly, because they can radiate energy away via the electromagnetic force, they can slow down and settle into dense, tightly packed structures. But dark matter, by definition, does not interact with electromagnetism.
Oh, I see.
It has no mechanism to efficiently radiate away its kinetic energy.
So when dark matter particles cross paths, they can't shed energy to slow down and bond. They just slingshot past each other indefinitely.
That is exactly the issue. And this is why dark matter halos around galaxies are incredibly diffuse and puffy. Yeah, puffy. The particles are moving too fast and have no way to cool down and condense. Therefore, the formation of highly ordered, complex dark matter structures like molecules, let alone a biological entity or a civilization, it seems highly improbable based on our current understanding of its thermodynamic limits.
But we don't know for sure.
Right. In theoretical physics, absence of evidence is not evidence of absence. There could be subcomponents of dark matter that possess self-interacting properties we just haven't modeled yet.
It's staggering, honestly. We are surrounded by this puffy, invisible architecture that fundamentally shapes our galaxy, and we only know it exists because of the dents it leaves in the space-time floor.
Yeah, it's humbling.
It really is. Now, to understand how gravity gave birth to both this elusive dark sector and our visible baryonic matter, we have to rewind the clock.
All the way back.
We have to peer into the ultimate time machine and look at the quantum origins of the universe.
The Big Bang and the subsequent inflationary epoch. Because if you want to understand the fabric of reality, you have to look at the exact moment the loom started weaving.
So let's delve into the actual physics of looking back in time. Because the term surface of last scattering, it sounds incredibly dramatic.
It does sound like a sci-fi movie.
Right. But it represents a highly specific thermodynamic threshold for roughly 380,000 years after the Big Bang.
Correct. You have to picture the early universe. It was not a sprawling, empty void.
What was it?
It was a remarkably hot, dense thermal bath, a coupled baryon-photon fluid. The ambient energy was so immensely high that atoms could not even form.
Because it was just too hot.
Too high, too energetic. Anytime an electron tried to bind to a proton to make an atom, a high-energy photon would immediately smash into it and blast it away.
Just break it apart.
Instantly. Which means the entire universe was filled with a dense fog of free electrons.
And because photons, which are particles of light, readily interact with free electrons, light could not travel in a straight line.
Not at all.
It was undergoing constant Thomson scattering. Like a photon would travel a microscopic distance, smash into an electron, and ricochet in a new direction. The mean free path of a photon was essentially zero.
The entire universe was basically an opaque, glowing plasma.
It's like the cloud analogy from the source material, right?
Yes, when you look at a cloud in the sky, you can't see inside of it.
Because the water molecules scatter the light.
Exactly. You only see the surface of the cloud where the light finally breaks free and reaches your eye. The universe works exactly the same way.
But the universe was expanding.
Right. And as the metric of space-time expanded, the thermodynamic temperature of this plasma began to drop. This is a direct consequence of adiabatic expansion. Eventually, the ambient temperature of the universe dropped below roughly 3,000 Kelvin.
Which is the magic number.
It is. At this precise thermal threshold, the photons no longer possessed enough kinetic energy to knock the electrons away from the protons.
This is the era of recombination.
Yes. The electrons finally settled into stable orbits around the protons, creating the first neutral hydrogen and helium atoms.
And the moment those free electrons were swept up into atoms, the fog lifted.
The obstacles were gone. The photons that were bouncing around in that plasma were suddenly free to travel in a straight line across the universe forever.
That is just, wow. So that exact boundary, the moment the universe became transparent, that is the surface of last scattering.
That's it. When we look deep into the night sky, we are looking at ancient light. The further away we look, the further back in time we see.
Right, because light has a speed limit.
Exactly. Eventually, our telescopes hit a literal wall of fog. We are seeing the exact moment that ancient light broke free from the plasma. We observe it today as the cosmic microwave background, or CMB.
And because that light has been traveling for over 13 billion years, and the universe has been expanding that entire time, the wavelength of that light has been stretched out.
Cosmological redshift.
Right. It started as this blistering, high-energy, visible and ultraviolet light, but the expansion of space has stretched it out into the microwave spectrum, which means we can use microwave satellites to take the literal temperature of the sky at the dawn of time.
And this is where observational cosmology achieved one of its greatest triumphs. Starting with the COBE satellite in the early 1990s, then WMAP, and ultimately the Planck satellite, we mapped this microwave afterglow.
And didn't the initial data present a massive problem for physicists?
Oh, a huge problem. When we measure the temperature of the CMB across the entire sky, it was uniform to an absurd degree.
How uniform?
It was exactly 2.725 Kelvin everywhere, in every direction, down to an accuracy of 1 part in 100,000.
Great, wait, explain why that's a problem. This is the famous horizon problem, right?
Yes. Think about it this way. If you look at one edge of the observable universe and then look at the exact opposite edge, they have the exact same temperature.
Right.
But they are separated by tens of billions of light years. They've never been in causal contact.
Meaning light hasn't had time to travel between them.
Exactly. They haven't had the time to exchange heat and reach thermal equilibrium.
So it's like pouring a cup of boiling water in New York and a cup of freezing water in Tokyo and having them instantly become the exact same temperature without ever touching.
It makes no physical sense. The only logical conclusion is that before the universe expanded, those two distant points must have been incredibly close causal contact. This is the cornerstone evidence for cosmic inflation. The idea that a fraction of a second after the Big Bang, the universe underwent an exponential, violent expansion, stretching a microscopic, thermally unified patch of space into the macroscopic universe we see today.
That is mind-bending. But you know, the true magic of the Planck satellite data isn't the uniform temperature.
No, it's the imperfections.
It is the tiny fluctuations, that 1 part in a 100,000 difference. Because if you subtract the uniform 2.725 Kelvin baseline, you get this map of microscopic hot and cold spots.
The seeds of the universe.
Right. And for a long time, the astrophysical community was fiercely divided on what actually created those spots. We had to debate whether these were caused by quantum fluctuations or by cosmic strings.
A huge debate.
Let's dig into that debate because I think it really highlights how brutal and precise physics can be.
Well, the cosmic string theory was an incredibly elegant model. In the late 20th century, many theoretical physicists posited that as the early universe cooled, it underwent phase transitions.
Kind of like water freezing into ice.
Exactly like that. When water freezes, you often get cracks or imperfections in the ice. In the universe, these imperfections would be one-dimensional topological defects,
Cosmic strings.
cosmic strings. The theory was that these immense, unimaginably dense strings whipped through the early plasma, gravitationally pulling matter toward them, and that's what seeded the formation of galaxies.
I mean, it sounds plausible. A network of heavy cosmic strings acts as the scaffolding for the universe.
It was a very popular idea. The Kibble mechanism dictates how these symmetry-breaking phase transitions would leave these topological defects behind.
But if cosmic strings were doing the heavy lifting, they would be an active source of gravity.
Yes, they would be constantly moving, constantly dragging matter around, creating a very chaotic, incoherent signature in the plasma.
Okay, so what was the competing theory?
In contrast, the competing theory argued for passive sourcing via quantum fluctuations.
Quantum fluctuation.
Yeah. In the quantum vacuum, space is never truly empty. Heisenberg's uncertainty principle dictates that pairs of virtual particles are constantly popping into existence and annihilating each other.
Out of nowhere.
Out of nowhere. During the violent epoch of cosmic inflation, these microscopic quantum fluctuations were suddenly stretched to macroscopic cosmological scales before they could annihilate.
So they got frozen.
They became frozen into the metric of spacetime as tiny, tiny variations in density.
So, on one side of this debate, you have cosmic strings actively churning the plasma. On the other side, you have quantum density fluctuations sitting passively, with gravity just slowly pulling matter into the denser pockets.
Right.
How did the Planck satellite definitively kill the cosmic string theory?
It all comes down to baryon acoustic oscillations.
Acoustic. Like sound.
Exactly like sound. Essentially sound waves traveling through the early plasma. When we analyzed the temperature fluctuations in the CMB using spherical harmonics, we were essentially looking at the power spectrum of these sound waves.
Okay.
If cosmic strings were actively churning the plasma, the power spectrum would look messy, incoherent, without distinct, sharp peaks.
Because it's a chaotic mess.
Right. But when Planck delivered the data, the power spectrum was stunningly crisp. It showed perfectly organized harmonic acoustic peaks.
So it looked like music almost.
A masterpiece of data. Those sharp peaks prove that all the sound waves in the early universe started oscillating at the exact same moment. They were perfectly coherent.
And cosmic strings couldn't do that.
Cosmic strings, being active and chaotic, could never produce such perfectly synchronized harmonics. The data conclusively proved that the seeds of our galaxies were not massive topological defects, but microscopic quantum glitches frozen into the sky by inflation.
Every supercluster, every galaxy, every star, and the carbon in your DNA is the direct gravitational result of a microscopic quantum hiccup at the dawn of time.
It is deeply humbling.
It really is. But establishing this timeline, relying on the physics of recombination and those acoustic peaks, it brings us to a massive, raging debate happening in astrophysics right now.
The age of the universe.
Yes, the age of the universe, because the James Webb Space Telescope went up, and it is actively threatening to break the calendar.
Well, science thrives on crisis, and JWST has certainly delivered one.
Give us the background on this.
For decades, the precision cosmology standard model, the lambda CDM model, pegged the age of the universe at 13.8 billion years.
Right, that's the number everyone knows.
And this was corroborated by CMB data, the expansion rate, and stellar evolution models. But JWST possesses infrared capabilities that allow it to see further into the high redshift universe than Hubble ever could.
Okay, for context for you listening, redshift, or the z-value, it basically measures how much the light from a distant object has been stretched by the expansion of space. High redshift means we are looking at objects incredibly far away and therefore incredibly young in the universe's timeline.
Perfect summary. Now, JWST has been finding galaxies at redshifts of z equals 10 and beyond.
Which is super early in the universe.
Extremely early. But these aren't chaotic, primitive clusters of stars.
Right, they aren't baby galaxies.
That is the anomaly.
Yeah.
JWST is observing massive, fully formed, structurally mature galaxies with developed metallicity existing just a few 100 million years after the Big Bang.
And why is that a problem?
Because, according to our established models of hierarchical galaxy formation, these galaxies simply did not have enough time to merge, accumulate mass, and organize into such complex structures. It is a cosmological impossibility based on a 13.8 billion year timeline.
Which led to this highly publicized paper by physicist Rajendra Gupta proposing a, frankly, radical solution.
Very radical.
He integrated a tired light model with covariant coupling constants, suggesting that the universe might actually be 26.7 billion years old, nearly double what we thought.
Yeah, his model argues that the constants of nature actually change over time, and that light loses energy independently of cosmic expansion.
Which would stretch out the timeline and give these massive galaxies plenty of time to form.
It's mathematically provocative, yes, but the broader astrophysical community is intensely skeptical.
Why, if it solves the JWST problem?
Because it comes back to the rigorous internal mechanics of the early universe. You cannot simply double the age of the universe without devastating other tightly constrained metrics.
Like the cosmic speedometer, Big Bang nucleosynthesis, or BBN.
It's exactly BBN. The early universe acted as a nuclear fusion reactor for a very brief, highly specific window. As the plasma cooled, neutrons and protons fused to create the first isotopes.
Okay.
But because neutrons decay rapidly, the ratio of neutrons to protons froze out at a very specific temperature.
So it's like a timer going off.
Physics of BBN are ironclad. The expansion rate of the universe dictates how fast it cools. If the universe took 26.7 billion years to reach its current state, the expansion rate in the early epochs would have to be fundamentally different.
And if the cooling rate changes?
The neutron-proton freeze-out happens at a different time, which fundamentally alters the primordial abundances of hydrogen, helium-4, deuterium, and lithium.
But when we actually measure the primordial gas clouds out there in the universe, the ratio of hydrogen to helium perfectly matches the 13.8 billion year expansion model, right?
Spot on. The Saha equation, which dictates the ionization state of the plasma during recombination, is also locked in. If you stretch the timeline to 26 billion years, you break the baryon acoustic oscillations we just talked about. You break the BBN speedometer.
The math just falls apart.
The local physics of the early universe, the thermodynamics, the atomic cross-sections, the cooling rates, they are completely mathematically cohesive. To fix the JWST galaxy problem by doubling the age of the universe is akin to fixing a leaky faucet by bulldozing the entire house.
Wow.
It is far more likely that our models of early star formation, perhaps involving direct collapse black holes or different dark matter dynamics, are flawed, rather than the foundational timeline of the cosmos.
So we are tweaking the recipe of how galaxies bake rather than changing the time the oven turned on.
That's a great analogy.
But, the mention of the oven turning on leads us directly into what I think is the most violent intersection of theoretical physics, philosophy, and epistemology.
Oh, absolutely.
Because whether the universe is 13 billion or 26 billion years old, you eventually have to confront the ultimate question. What was there before the clock started?
The problem of nothing.
Yes.
When cosmologists and physicists attempt to model the initial singularity, or the quantum state preceding inflation, we really run up against the limits of human cognition and language. De Rham points out that mathematically the most probable state of reality is non-existence.
Which is terrifying.
It is. The fact that an intricate, highly ordered universe exists is the ultimate thermodynamic and quantum anomaly.
I have to push back on the concept of nothing, though, because the way it is often communicated in pop science is deeply flawed, in my opinion.
How so?
Well, when people hear the universe came from nothing, they immediately imagine the quantum vacuum. They picture empty space, void of matter, where quantum fluctuations are just bubbling away. But the quantum vacuum is emphatically something.
Very true.
It has energy, it has geometry, it has rules. True nothingness is not an empty room. It is the absence of the dimension required to even host a room.
You're touching on the exact friction point of quantum cosmology. The Wheeler-DeWitt equation, which is an attempt to mathematically describe the quantum state of the entire universe, notably lacks a time parameter.
No time.
In the Hartle-Hawking state, or the no-boundary proposal, time as a chronological progression loses its meaning as you approach the initial singularity. Time becomes a spatial dimension.
Which means asking what happened before the Big Bang is physically meaningless.
It is grammatically identical to asking what is further north than the North Pole.
Oh, I love that.
The geometry of the coordinate system just does not allow for it. The concept of "and then" implies a chronological flow that had not yet been generated.
Right.
If space-time is an emergent property of quantum entanglement, as many modern holographic theories suggest, then nothingness is simply a state where the quantum information has not yet structured itself into a geometric manifold.
That concept absolutely shreds the human desire for a narrative structure.
It really does.
Because we want a protagonist and an author. When we look at the fine-tuning of the universe, the exact mass of the electron, the precise strength of the strong nuclear force, the fine structure constant, if any of these were altered by a fraction of a percent, matter couldn't form.
Stars wouldn't ignite.
Life would be impossible. It is mathematically terrifying to look at that perfection and accept it as just a random quantum anomaly. We want to believe in a puppet master.
And this is the crux of the anthropic principle, a concept that divides physicists bitterly.
Explain the anthropic principle.
So the strong anthropic principle suggests the universe is somehow compelled to eventually have conscious and sapient life emerge within it. But the dominant perspective in modern theoretical physics, particularly when viewing the string theory landscape, is much more pragmatic.
Okay, pragmatic how?
Well, string theory allows for something like 10 to the 500th power different vacuum states.
That's an incomprehensible number.
Essentially, it's 10 to the 500th power different mathematical ways to structure a universe, each with different physical constants.
So we aren't a finely tuned masterpiece created by a puppet master. We are just one universe out of an infinite multiverse of failures.
We are a happy accident.
A happy accident.
The overwhelming majority of those universes might collapse instantly or expand so violently that atoms never form. There is no external intelligence required to fine-tune our specific universe.
We're just the ones that worked out.
The only reason we are observing this exact, seemingly perfect configuration is because any other configuration wouldn't allow biological observers to evolve to see it. The universe doesn't have a purpose for us. Our existence is just a localized, chaotic consequence of the mathematical parameters we happen to be sitting in.
And what's fascinating is how profoundly that philosophical perspective, finding beauty in chaos and accepting that our purpose is self-inflicted rather than divinely mandated, is reflected in the incredibly unique life of the physicist we are following today.
Claudia de Rham.
Yes, Claudia de Rham's approach to the universe makes total sense when you examine her anthropological background.
De Rham's origin story is essential context for her work. She was not raised in the insulated corridors of Western academia.
Not at all.
She was born in Switzerland, but her parents were deeply embedded in sustainable development and diplomatic work in the global south. She lived in Ayacucho in the Peruvian Andes.
Wow.
She lived in Iquitos, a city completely landlocked by the Amazon rainforest. She spent her formative teenage years in Madagascar.
Her family was executing boots-on-the-ground survival and development projects, preventing deforestation, building sustainable agriculture, educating children in deeply remote areas.
Extremely remote.
And if we look at the sociological impact of that upbringing, it fundamentally alters your epistemology.
Oh, absolutely.
If you grow up in a Western metropolis with an iPhone, your definition of purpose is highly individualized. It's about your career, your ego, your status. But if you were living among remote communities, sometimes villages of maybe 150 people, relying strictly on the agricultural harvest to survive the season, purpose is stripped of its ego.
In those environments, survival dictates collectivism. Purpose is immediate, tangible, and highly localized.
Exactly.
You realize that humanity is just a biological species fighting for equilibrium in a deeply unforgiving environment. It removes the illusion that humans are the center of some grand, cosmic narrative.
But here is the ironic twist that I find so compelling. With all that exposure to raw, vibrant biology, the unparalleled biodiversity of the Amazon basin, the endemic species of Madagascar, she chose theoretical physics over biology. Why?
Because biology, for all its beauty, is governed by chaotic, nonlinear dynamics.
It's messy.
It is incredibly messy and localized. An ecosystem in the Andes operates on wildly different parameters than a rainforest in Madagascar. Biological evolution is subject to a million microscopic, localized variables. To a mind-seeking fundamental truth, biology is too localized.
It changes depending on where you stand.
Right. Physics, however, relies on mathematical symmetries.
Noether's theorem.
Exactly. Every continuous symmetry of the universe yields a conservation law.
So, no matter where de Rham traveled on the planet, whether she was standing at high altitude in Peru or at sea level in Madagascar, the physical laws remained perfectly invariant.
Lorentz invariance dictates that the laws of physics are the same for all observers in inertial frames. Gravity pulls with the exact same mathematical precision anywhere on Earth.
And for someone whose cultural and geographic reality was in constant chaotic flux, the unshakable universal constants of physics provided like a psychological anchor.
It's a beautiful way to look at it.
And if you were hunting for the ultimate unshakable anchor in physics, you inevitably collide with the king of constants, Albert Einstein.
Of course.
The 1915 theory of general relativity is, as de Rham points out, still the best game in town. The scale of its success is mathematically staggering. The literature points out that general relativity has been rigorously tested over 18 orders of magnitude.
To contextualize 18 orders of magnitude for you listening, it represents a scale that bridges the microscopic and the cosmic.
Give us the extremes.
Well, we have validated the inverse square law of gravity at distances as small as a few tens of micrometers using incredibly precise torsion balance experiments, like those conducted by the ITWASH group.
Tens of micrometers, that's tiny.
They use pendulums separated by a gap thinner than a human hair to prove that gravity behaves exactly as Einstein predicted at microscopic scales.
And on the opposite end of those 18 orders of magnitude,
We have LIGO, the Laser Interferometer Gravitational Wave Observatory. We use 4-kilometer-long laser beams to detect the infinitesimal rippling of space-time caused by two supermassive black holes merging millions of light years away.
it's just unbelievable.
And the exact same tensor calculus that governs the micrometer torsion balance flawlessly predicts the gravitational wave signature of colliding black holes.
It is the pinnacle of scientific achievement. In fact, we actually understand the mechanics of gravity better than we understand the mechanics of light.
We do.
That feels deeply paradoxical to me because electromagnetism light, it feels so tangible. I can turn on a flashlight, I can block it with my hand. Gravity is invisible.
But that ability to block light is exactly why gravity is more mathematically pure.
Oh, interesting.
Electromagnetism can be shielded. A photon can be absorbed by an atom, scattered by a plasma, or bent by a prism. The electromagnetic field is constantly interacting and being obstructed by matter.
Right.
Gravity, however, cannot be shielded. There's no such thing as a Faraday cage for gravity.
Because you can't block geometry.
Exactly. The curvature of space-time permeates everything seamlessly. Because it interacts with all mass energy universally, its signature is clean, unshielded, and mathematically perfect.
But, and this is where physics gets delightfully terrifying, general relativity is incomplete.
Yes, it is.
It is a classical theory. It works flawlessly for 18 orders of magnitude, but when we push it into extreme environments where quantum mechanics and immense gravity collide, the math breaks down into infinities.
Singularities.
Right, the center of a black hole or the exact singularity of the Big Bang. This is where physicists have had to look for dualities and specifically the holographic principle.
Now, this is where it gets truly mind-bending. The holographic principle, which is derived heavily from string theory and the ADS-CFT correspondence, suggests something completely radical about black holes.
Break it down for us.
So, a black hole is the ultimate gravitational powerhouse. But in certain theoretical frameworks, the three-dimensional volume of a black hole, along with all its extreme gravitational physics, can be entirely mathematically described by a two-dimensional surface on its boundary that has absolutely zero gravity.
Let me just unpack that, because this is where theoretical physics sounds like literal magic.
It really does.
We are talking about the Bekenstein bound and Hawking radiation here. When matter falls into a black hole, the quantum information of that matter isn't destroyed, right? Because that would violate quantum mechanics.
Correct. Information cannot be lost.
Instead, it is scrambled and stored on the two-dimensional event horizon of the black hole.
And the math takes that even further. The ADS-CFT correspondence shows that a universe with gravity, the anti-de Sitter space in the bulk, is mathematically identical to a conformal field theory, a quantum theory, with no gravity living on its boundary.
So gravity's just an illusion.
It implies that the intense space-time warping gravity inside the black hole is simply a holographic projection of quantum interactions happening on a flat 2D surface. Physicists actually use the math of extreme condensed matter physics, like the behavior of superconductors on a flat plane, to solve the gravitational mysteries inside the black hole.
It fundamentally suggests that our 3D universe and the gravity we experience might just be a holographic projection of quantum data interacting on a lower dimensional boundary.
It's an incredible thought.
It really is. So to solve the limits of Einstein, we have to look past 4D spacetime. We have to retain general relativity but extend it into extra dimensions. And this is exactly where Claudia de Rham shattered 80 years of accepted dogma. Let's dive into massive gravity.
Okay, to understand the controversy of massive gravity, We have to look at the force carrier of gravity itself.
The graviton.
Yes. In the standard model of particle physics, forces are mediated by particles. Electromagnetism is mediated by the photon, the strong nuclear force by the gluon. Gravity is theoretically mediated by a spin 2 particle called the graviton.
And for decades, the foundational assumption was what?
That the graviton, like the photon, must have exactly zero mass. It must be completely massless.
But de Rham asked the heresy, what if the graviton has a mass? What if it is incredibly tiny, but non-zero?
And the reason that question was considered theoretical suicide is because of the Fiers-Pauli limit, established in 1939, and the subsequent theorems built upon it.
80 years of dogma.
80 years. The mathematical dogma stated that if you give the spin 2 graviton a mass in a nonlinear theory, it introduces extra degrees of freedom into the math. Specifically, it introduces a scalar mode that acts as an Ostrogradski instability.
And in the physics community, this fatal instability is known as a ghost.
A ghost, yeah.
We need to rigorously define what a ghost is in quantum field theory, because we aren't talking about a paranormal entity. We're talking about a particle with a negative kinetic energy term.
Right. Which sounds impossible.
In our standard universe, kinetic energy is always positive. A moving baseball has positive kinetic energy. If a particle has negative kinetic energy, it's Hamiltonian way. The total energy of the system is unbound from below.
That implies a catastrophic unraveling of reality.
Why?
Because the conservation of energy states that the total energy of a closed system remains constant. If ghosts exist, the quantum vacuum could spontaneously decay.
Spontaneous.
Yes. The universe could create a positive energy particle, like an electron, and simultaneously create a negative energy ghost. 1 plus -1 equals 0. The energy total is 0.
Which means the universe has found a loophole to cheat the conservation of energy.
Exactly. It would instantly and infinitely populate itself with matter and ghosts, exploding in a catastrophic cascade of radiation. Reality as we know it would instantly destroy itself.
Because the math clearly showed that massive gravity created these universe-destroying ghosts, physicists just shut the door on the concept. It was a dead end. Massive gravity equaled ghosts. Case closed.
But de Rham refused to accept the finality of that dogma.
How did she approach it?
She approached the problem by relaxing the assumptions of our four-dimensional space-time and incorporating extra dimensions using brain cosmology.
Brain cosmology is brilliant, and the analogy de Rham uses the water bug. It perfectly illustrates how it operates.
I love the water bug analogy.
Yeah, so imagine we are highly intelligent water bugs that live entirely on the surface tension of a pond. We can move forward, backward, left, and right. To us, the universe is strictly a two-dimensional plane. We do not have the sensory apparatus or the mathematical vocabulary to even conceptualize down.
But beneath that two-dimensional surface, the brain, there is a deep three-dimensional volume of water, the bulk.
There are fish swimming, currents moving, bubbles rising.
As water bugs, we cannot see the bulk. But when a bubble rises from the depths and bursts on the surface tension, we experience it as a sudden, inexplicable injection of energy on our 2D plane.
So in this model, our observable universe is a 3D brain floating in a 4D or 5D bulk. The extra dimensions are the deep water.
Right.
And we actually see the mathematical hints of this deep water in particle colliders. When physicists smash two particles together at incredibly high velocities, they meticulously measure the energy before and after the collision. And sometimes a tiny fraction of the energy is just missing.
And the conservation of energy dictates it cannot be destroyed. So where did it go?
It leaked.
Exactly. In theories like the DGP model, the Dvali-Gabadadze-Perotti model, the collision is so violent that the energy leaks off our 3D brain. It transforms into gravitons that propagate out into the extra dimensions into the bulk. We observe it as missing energy, but it simply leaked into the basement of reality.
By utilizing the mathematics of these extra dimensions and meticulously tuning the interactions of the massive graviton, de Rham, alongside her collaborators, found a loophole.
They developed the DRGT massive gravity theory.
She found a specific mathematical framework where the graviton could have mass and the extra degrees of freedom could be hidden through a process called Weinstein screening.
Entirely eliminating the catastrophic ghost instability. Massive gravity could exist without destroying the universe.
But the psychology of that discovery is perhaps the most fascinating aspect of her journey. When she first balanced the equations and saw that the ghosts were eliminated, her immediate reaction was not triumph.
It was imposter syndrome.
She assumed she had made a basic arithmetic error.
Because in theoretical physics, you build your research on set zero. Set zero is the foundational bedrock established by the geniuses who came before you. It is the assumptions you accept as truth, so you don't have to rederive the entirety of mathematics every single morning.
Right. And to realize that set zero is fundamentally flawed is deeply isolating.
When you stare at an equation that contradicts 80 years of consensus accepted by Nobel laureates, you do not feel like a visionary. You feel profoundly foolish. You assume there is a massive, obvious flaw in your logic that everyone else has already seen and dismissed.
It takes an immense amount of intellectual courage to publish that paper and tell the community that the bedrock they've been standing on is cracked.
But she wasn't foolish. The previous generations had made a specific assumption in their nonlinear expansions. And when she relaxed that assumption, the mathematics of the universe opened up in an entirely new direction.
It is a stunning reminder of how fragile settled science really is, which brings us to the core takeaway for you listening today.
The ultimate lesson of this deep dive is epistemology, how we know what we know. The mechanics of the cosmic microwave background, the debates over the age of the universe, the mathematics of massive gravitons, these are all essential frontiers.
But the broader application is the absolute necessity of critical thinking. Science is not a catalog of absolute truths. It is a continuously evolving model of falsifiable hypotheses.
If the greatest minds in theoretical physics can blindly accept a flawed mathematical theorem about gravity for 8 decades, what assumptions are you making in your own life?
What settled facts about our society, our economics, or our own personal limitations are built on mathematical models that are slightly off? Knowledge is most valuable when we actively recognize its limits.
Progress requires the bravery to question the foundational assumptions of the systems we operate within. You have to be willing to look at the bedrock and ask if the premise is still sound.
So as we conclude this deep dive, I want to leave you with one final, lingering thought built on everything we've unpacked today. We spend so much of our time as individuals and as a civilization staring up at the cosmos, desperately searching for some grand external purpose.
We want the universe to provide a puppet master. We want a narrative.
But what if the profound, terrifying, and ultimately beautiful reality of our existence is simply this? We are the hyper-intelligent water bugs floating on the surface tension of a multidimensional pond. We have absolutely no inherent purpose given to us by the pond itself.
Just physics.
Just physics. Yet through billions of years of cosmic cooling, thermodynamic expansion, and localized quantum accidents, we were gifted with the incredibly rare, fleeting ability to look down at the water and wonder just how deep it goes.
A phenomenal synthesis. The purpose isn't found in the answers. It is found in the courage to keep asking the questions, keep wondering, and never stop questioning the floor beneath your feet.
We'll catch you on the next deep dive. Stay curious.